Hello everyone from Math 1340, Statistics. It's Professor Wenson here again with a video on your KnewtonAlta homework. I've titled this one a Chapter 7 KnewtonAlta Section, the Central Limit Theorem for Proportions. And the reason this one doesn't have any specific section number is because there is no section in your OpenStax statistics book that covers this, but it's still a topic we need to cover in our course outcomes and objectives at Macomb. Now it is covered, and I do have, and I do in your Canvas page for this section, I have a link. There is a section 7.3 in the OpenStax Introductory Business Statistics that does cover this topic, and let me show you that here. This is the Introductory Business Statistics book from OpenStax, and their section 7.3 is this central limit theorem for proportions, and they cover it. And I would like you to, and I have a link to this, and would like you to read this, of course. All right. So now we've seen the central limit theorem for means, right? In the first couple sections of chapter 7. This is a similar concept, but instead of taking the means of samples, averages, we're going to be finding what are called proportions. And a proportion is just a percentage of successes. Right? And I'll write that out. I'll write all this stuff out. I'm going to go through an example with you, showing you a sampling distribution for proportions. Right, so this first objective, and there are 5 of the objectives in this, but you'll see the 2 objectives are just the same as 2 other ones, but with a calculator. All right, so I'm just going to show you how to do the calculator right from the get-go. So understand sampling distributions and the central limit theorem for proportions. All right, so first time I'm seeing this, I'm going to go to more instruction, view instruction. Okay, so some definitions here. So in statistics, proportions are the fraction of a population or a sample that are successes. All right, we'll get to that. Proportions are typically used with binary data, such as yes, no, or pass, fail, or success, failure. The total number of objects are known as trials and are denoted by the variable n, whereas the number of objects that possess the characteristic of interest are known as successes, denoted by the variable little x. You've seen similar stuff to this before in chapter 4 when we talked about the binomial distribution. Right, so a population proportion will be denoted by just a lowercase p, and it's equal to the number of successes in the population divided by the population size, right, x over n. And the same formula goes for a sample proportion, but they use different notation. A population proportion will be represented by lowercase p, and a sample proportion will be represented by this p with a caret over it, or sometimes called p hat. And it's the same calculation though. It's the number of successes in the sample divided by the size of the sample, x over n. All right, so remember, it is important to remember that p hat is an estimate of the population proportion p. Sometimes it is referred to as a point estimate. So we'll get into that stuff in chapter 8 when we talk about creating what are called confidence interval estimates for a proportion for a parameter. But for right now, don't worry about the words point estimate at the moment. Just know population proportion, sample proportion. All right. So they give you an example here. I'll read through this one. So suppose the researcher is interested in proving that people on parole are more likely to be reconvicted of a second crime than not. So in a study of 50 inmates who were released from prison on parole, the researcher found that 30 of them had been reconvicted of a second crime within 2 weeks of being released. So in this example, there are, 50 trials, 50 inmates, the size of the population, right, the entirety of the 50 was n 50, and then x were 30. Here successes, what the researcher's interested in is how many get reconvicted. Right, so success here is being reconvicted of a second crime, which doesn't sound good, but like it's still what the researcher is interested in, so if it happens, it's considered a success. And there were 30 of those, right? So then the population proportion P is 30 out of 50, right? 30 successes out of the 50 trials, out of the size of the population, or 0.6, 60%, right? A proportion is just percentage of successes. All right, so let's say the same researcher chose 30 out of the 50 original inmates, so a sample, right? The population was the 50 inmates. She takes 30 of them, all right? So a sample, and found out that of those 30, 25 were convicted of a second crime within 2 weeks of being released from prison. So now we have a sample from our original population. So this is a sample proportion denoted by p hat, right, with a little wedge, a little caret above it. Same calculation though, it's 25 successes, 25 convictions out of the sample size of 30. All right, so approximately 0.83, 83% would be the sample proportion. Okay. Like I said, a success is not always a good thing, like being reconvicted of a crime. Success is just what you're interested in. All right. So next is on a distribution of sample proportions. So we did this before with means, sample means, and there were those sections on the central limit theorem for sample means, where you had a population. You pulled samples out of that population and then looked at the mean of every single sample. And then that created its own distribution, right? The distribution of the sample means. We're going to do the same thing here, but with sample proportions. So as we were for sample means, we are interested in the distribution of possible sample proportions for a given sample size n. This sampling distribution for the sample proportion p hat has a mean, mu sub p hat, the mean of the proportions, the average of the sample proportions, and a standard deviation, right, the sigma p hat, or the standard deviation of all these sample proportions. All right. And what you're going to find is that the mean of all the sample proportions will be equivalent to the population proportion, P. And the standard deviation of all sample proportions will be the square root of the population proportion times 1 minus the population proportion divided by the size of your samples. Right, all that under the square root. You could call it PQ over N or P times 1 minus P over N. All right. And they give me an example down there. Let me do an example of my own. All right, I'm going to do an example of my own where we take a look at the distribution of sample proportions, all right, on a piece of paper. Okay. So suppose my population is made up of just a few numbers, with the numbers 1, 2, 3, and 4. And I don't, and it has an unknown distribution. Maybe a uniform, say I have an equal amounts of 1, 2s, 3s, and 4s in my population, but the population is made up of only the numbers 1, 2, 3, and 4. Now, let's say, a success in this scenario is going to be being a number less than 3. Being less than 3. Right? So then the population proportion which is denoted by this, just lowercase p, is, again, the number of successes. Here I'm considering a success, right, being less than 3. That'd be there's only 2 numbers in here less than 3 out of the 4, right? 2 out of 4, or a half, right? 0.5. So that's the population proportion. So now what I'm going to do is from the population. Now I'm going to do small samples because I don't want to write too much. I'm going to take samples of size 2. And we're going to look at all possible samples of size n equals 2, of size 2, where I can repeat values. Okay, let's say I can repeat values. And then their proportions. Now, if I'm taking samples of size 2, and there are 4 choices each time, that'd be 4 choices for the first object and then 4 choices for the second object. That's 16 samples of size 2, 4 times 4, right? The fundamental principle of counting. So that's why I wanted to do a small number here, because I'm going to be making 16 different samples for you. And actually I'm going to write out the first few and then I'll just pause the video and come back when I'm done with all 16. But if I took just a sample of size 3, then there'd be 64, 4 times 4 times 4, 64 different samples of size 3 I could take. And I don't want to write all that out. Right? So that's why I'm doing a very simple one. So I'm going to make a little table here. I'm going to do samples, and then their proportions. Remember, proportion is, for a sample, is denoted by this p hat, this p with a little wedge over it. So the first, let's say I take 1 and 1. Right, there's a sample of size 2 taken from those population values. Now, what proportion of this sample is a success, right? Is less than 3? Well, 100%. The p hat equals 1. Right? P hat equals 1. 2 out of 2. Two of those numbers are less than 3, and the size of the sample is 2. Another sample I could take is 1 and 1 then 2. Right? I could take 1 then 2. I guess technically I should be putting parentheses around these, but whatever. And again, less than 3, both of those are. So p hat equals 2 out of 2, or 1 again for that. And then I'm going to stop putting the brackets and braces. I could do 1 then 3. Now this time, this sample of 2, only 1 out of the 2. Right? So 1/2, or 0.5, is the proportion, the p hat, for that sample of 2. And then I could do 1 and then 4. So again, it's 1/2, or 0.5. And I could do 2 then 1. So again, this is a proportion of 1. 2 then 2, proportion of 1, right? Both of those are less than 3. And that's what, 6. There are 10 more I need. So I'm going to pause it and come back when I have them all written out. And we'll look at all the proportions. Okay, so I've written all those out. So here's all 16 different ways I could pull 2 values from 1 through 4. All 16 possible samples of size 2. And the proportion of successes, and here again, here I counted success as being less than 3, right? It depends on how you count a success. So 1, 1, half, half, 1, 1, half, 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 for these samples here. Then 0, 0, right? 3 and 3, 3 and 4, none of those are less than 3. So the proportion 0, 0 out of 2. Half, half, 0, 0. Now, what I'm going to do next, we're going to look at the distribution of the p hats. We're going to look at these numbers, right? all the proportions, all the p hats, and look at what's the mean of these p hats. Right. So remember how to find. Now there's only 16 of these. It's not that many. So remember how to find the mean of a set. And you add them up, divide by how many there are. So that's 1 plus 1 is 2, 3, 4, 5, 6, 7, 8. 8 is the sum of all those values, and then you got some zeros. Divided by, there are 16 of them, and look at this. 8 out of 16 is 0.5. I remember what I said earlier, right? Remember I pointed that out earlier, a little formula. The mean of the proportions, the mean of the sample, all the sample proportions is going to be exactly the same as the proportion of the population. And that's exactly what we're seeing here. So mu p hat, the mean of all the sample proportions, is p, the population proportion, 0.5. All right, then the standard deviation of these 16 sample proportions. All right. Now remember, you could do the deviations squared, add them all up, and then divide by, I'm pretty sure you would divide by 16 here, because this is all possible populations. Now I'll pull up a calculator. We could do this, all right. I could take the deviations, right, subtract the mean from all these, and square them. So let's see, I'd have 1, 2, 3, 4, 5, 6, 7, 8. I'd have 8 values where it'd be a half or negative half, and then squared. So I'd have 8 values times, times a half squared. I'd have 8 of those, half or negative half squared. Let me count that again. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, and then the rest of them, 0.5, all the 0.5s. When I subtract the mean, when I subtract 0.5, would be nothing. So here's the sum of the squares of the deviations is 2. Okay. And then I would divide this by 16. I divide this by the whole, this is a population here. This is all possible p hats. So I divide this by then 16, and then take so there's the variance, and then I would take the square root of this, and we're getting approximately. So again, this is the square root of 0.125, which is approximately 0.35. Let's say 35. Okay. Now, remember that little formula I put up earlier? I showed you earlier. The standard deviation of all these p hats will be the square root of p times 1 minus p, right? The population proportion times 1 minus the population proportion, divided by the sample sizes. Well, let's see. That's the square root of 0.5 times 1 minus 0.5 divided by 2. Right, all these samples were size 2. That's the square root of 0.5 times 0.5 is 0.25, then divided by half is 0.125. Hey, look, it is exactly the same. So this formula works for the standard deviation of all these sample proportions. And then I could even make a graph of the sample proportions. Right? We can make a little histogram. Right, this will be the last thing. Right? So here's a histogram for all these sample proportions. So the horizontal axis represents possible values of the sample proportions, and then we'll do frequencies up here. You could even do probability if you wanted. I guess I'll do probability as well. You know, we could make a table. We could make a table. Here are p hats, different values of p hat, and then what's the probability of getting that particular value of p hat when we have these sample sizes of 2. Now all the p hats that show up here are either 0, 0.5, or 1. Right? You look at this group of all the p hats I had. They're either 0, 0.5, or 1, and there are 16 of them. The probability of getting a p hat of 0 was, 4 out of the 16, or 0.25. The probability of getting a p hat of a half was, there were 1, 2, 3, 4, 5, 6, 7. There were 8 of those. 8 out of the 16. That's a half. And the probability of getting a p hat of 1, there were 1, 2, 3. There were 4 out of 16 of those. 0.25. So here's, 0.25. So again, here's probabilities of getting those p hats. 0.25, and then 0.5 here, and then I can make little bars. So here's 0, and then you got 0.5 and 1, and making little bars around these, so that the values are in between here. We're getting this distribution. Now this was only for samples of size 2. So there's only 3 bars showing up here. But what we're going to see is that the larger I make n, the closer this gets to being a normal distribution. Like, you can see the symmetry. You can use, like we did with the binomial in the last section, we're going to be able to use a normal distribution. This is a normal curve here that I'm drawing, a symmetrical bell shape. We can use a normal distribution to approximate these. And the larger n gets, the closer this graph will get, to being like the normal curve, right? Like a very smooth normal curve. This isn't very smooth right now. It's 0.25 to 0.5 to 0.25. It's just very jagged, very sharp rises and sharp falls. But the more, if I took samples of size 100, which I wouldn't want to do, it took me a long time to just do 16 here. If I took samples of size 100 and made a histogram for all the possible values of p hat that come up, that histogram would look very, very close. The top, if you looked at the tops of the bars, would look very, very close to forming a normal curve. All right. Okay, but that's what the central limit theorem for proportions tells us, right? The larger n gets, right, the closer to normal the distribution of the sample proportions will get. All right, so here's the central limit theorem for proportions. And again, that's abbreviated CLT a lot of the times for proportions. So say we're given a population, given any population, given population with proportion p, right, with proportion p, with proportion of successes p. 1, if the population has a normal distribution, then the distribution of the p-hats, then the distribution of the p-hats will be normal. Right, again, if you're you're taking samples of size n out of this population, right, you're taking samples of size n out of this population and looking at what, the p-hats, you're looking at the proportions. The distribution of all those sample proportions would be normal with a mean of p and a standard deviation square root of p times 1 minus p over n. All that under the square root. Right? And again, this is called, the mean of all the proportions, mu p hat. This is called the standard deviation, right? That's the standard deviation of all those sample proportions, or sigma p hat, or sometimes referred to as the standard error, as you've seen. Or if you're pulling sample sizes that are large enough, right? Remember that, kind of like for the central limit theorem for means. If you're pulling sample sizes large enough, and also they might add on the caveat that n times p and n times 1 minus p are both greater than or equal to 5. You might see that condition thrown up as well, because if these two are happening, then the histogram, like I drew here, then the histogram, if n times p and n times 1 minus p are greater than or equal to 5, the histogram will look more normal instead of being skewed right or skewed left. So then if your sample sizes are large enough and certain conditions are met like this, then this will also happen. P hat will still be approximately a normal distribution. The distribution of all the sample proportions will be approximately normal with a mean of p and a standard deviation of the square root of p times 1 minus p over n, or p times q over n. You might see that q written as well. This is huge, okay? All right, so after all that, let's go back and explain all that here and give you examples. You can look at histograms and how the larger n gets, the closer and closer these histograms will get to forming a bell shape. And then here it is, the central limit theorem. Okay, so their condition isn't that. So I've seen in other books the condition I wrote here with the n times p and n times 1 minus p being greater than or equal to 5. They have the condition n times p times 1 minus p is at least 10. All right, so you got to check that as well. All right. So here it is written out again, the central limit theorem for proportions. All right. For proportions. I don't know why they doubled that, but so suppose a simple random samples of size n are drawn from a population with proportion p. Then the distribution of those sample proportions, the p hats, is approximately normal with a mean equal to p and a standard deviation equal to the square root of p times 1 minus p over n. And as the sample size gets larger, the more normal it will become, right? And this holds provided that n times p times 1 minus p is at least 10, right? And that's going to imply that our sample sizes are large enough, right? As if this number is bigger than 10, or at least 10, that would imply that our sample sizes are large enough for the distribution to be close to normal. All right, then they read through an example here. I'm just going to get to a problem. Okay, so from recent survey data, it is known that the proportion of adults in the United States who are smokers is 18%. So that's our P. P is 0.18, right? The population proportion, the proportion of all adults in the U.S. is 18%. So being a smoker here is a success, right? What's of interest here is being a smoker. All right, so for a random sample of size 150, so this would be the n, what is the standard deviation for the sampling distribution of the sample proportions? So what's that standard deviation for the p hats, right? For if you were to look at all possible samples of size 150, take 150 people, 150 people, 150 people, and say, hey, what proportion of this sample smokes? What proportion of this sample smokes? What proportion of this sample smokes? And you did that for all possible samples of size 150. And then you looked at all those p hats, all those sample proportions, and made a histogram, or like I was doing with the samples of size 2 a minute ago. What would be the standard deviation for that group, that all those p hats, that sigma p hat? All right. So again here, very simply, I'll pull up my calculator. The standard deviation for the distribution of p hats is going to be the square root of p, which here was 0.18, right? They said the population proportion was 18%, times 1 minus p, so 1 minus 0.18, that'd be 0.82. And then, that product divided by the sample size. Now the sample sizes here are 150. And all of that should be underneath the square root. 0.18 times 0.82 divided by 150, all underneath the square root. So here would be the standard deviation for our p hats. Okay, 0.03. It says to 3 decimal places, so 0.031. So back here I'm entering 0.031 as the standard deviation for the distribution of those sample proportions. Okay. Again, they go through the same formula that I just went through. Good. Okay. So another question related to the same thing, where they want multiple values now. So you see they're asking here for what's the population proportion, and then if you were to take samples of size 40 out of the population and look at all possible, if you were able to look at all possible samples of size 40 and the proportion, the p hat for all those samples, what would be the mean of all those p hats? What would be the standard deviation of all those p hats? That's what's being asked here. So a small community college has a population of 986 students, 252 of whom are considered non-traditional students. Find the population proportion of being a non-traditional student is a success here, as well as the mean and standard deviation of the distribution of those sample proportions for samples of size 40. Okay, so I'll pull the calculator up. They're asking us to round all my answers here to 3 decimal places. All right, so what's the P? What's the population proportion of non-traditional students? Well, there are 252 non-traditional students in this population, and the size of the population is 986. So 252 divided by 986 into 3 decimal places rounded would be 0.256, right? Because you got 5.5, that would bump the third decimal place up to 5.6. So the value of p rounds to 0.256. Oh, and another thing, proportions, percentages, they're going to range from 0 to 1, right? You're never going to get a value of p less than 0, and you're never going to get a value of p greater than 1. All right, so please keep that in mind as well. All right, and then if you're taking all these samples of size 40 and looking at their proportions, the p hats, the mean of all those p hats should be the mean, the same as the proportion of the population. So the mean of all the p hats is going to be 0.256, the same as the population proportion. And the standard deviation of all those p hats, again, was that formula, right? The square root on the calculator here of p, so well, you know what, I'm just going to take the previous answer, just go second answer, times, and then in parentheses here, 1 minus the previous answer, right, that population proportion, and then divided by the sample size, which is 40. And again, make sure all of that is inside the square root. And we're getting a standard deviation of 0.069, right, if I'm rounding to 3 decimal places. So 0.069. Wonderful. Okay. All right. So hopefully, again, so it's kind of like for means, right? The central limit theorem for means, you just had to remember how to calculate the mean value of all the sample proportions and the standard deviation value of all the sample proportions. You just need to remember how to do that. Okay, so this is no different. Okay, so I've already done one like this. I'm not going to do this one. You know, you're given a P, you're given an N. So, and then you're asked to find, what's the standard deviation for the distribution of the proportions, right? What would be the standard deviation of all the P hats for samples of size 490? Right? So again, I've already done a couple problems like this. I'm going to cheat on this and let you work on something like that. Okay. And again, always, try to remember to read, read carefully. Remember see how they want you to enter answers, rounded to 3 decimal places and all that. And then we have one. It looks like one more problem here that's exactly like one I did earlier. So I'm gonna cheat on this one. I've already done something like this. Just keep going, move a little faster here. Okay. Right. So the next topic. Next objective is use the central limit theorem for proportions that I've shown you, to find probabilities, right? So now this is going to be finding area under a normal curve, right? We're going to see that the distribution of these p hats, these sample proportions, is a normal distribution. So you have this normal curve, and then we're going to find probabilities, meaning find areas under these normal curves. Now, there's one objective where you're doing it with the tables, right? Z-scores and everything, you're going to have to convert to Z-scores. And then there's another objective where you're doing the same thing using a calculator. And I'll show you how to do both right now. Right? So that way when we get to that objective, you've seen how to do it already. All right. So here, this question. A kitchen supply store has a total of 642 unique items available for purchase. Of their available kitchen items, 260 are kitchen tools. The store manager would like to study this further when conducting item inventory. If the store manager surveys 52 store items, what is the probability that 24 or fewer of them are kitchen tools? All right, so being a kitchen tool is a success. Okay. So, on a piece of paper, I'm going to draw pictures and write this stuff out here for this particular problem. All right, so for this problem, a success is, being a kitchen tool. And for the population, right, right, all the unique items in this store, the population proportion, right, the P, is how many of the items in the store are kitchen tools. That was 260 of them, divided by the 642. Right, so this is approximately, so I'm going to go here to pull my calculator up. 260 divided by 642. All right, so it's approximately 0. Let's go 404,984. So a little over 40% of the items in this store are kitchen tools. Now, that was for the entire population. What this guy is doing, this store manager, person, they're pulling 52 of these items. So I pull a sample of size, n equals 52. Now, we got to check. Remember that one condition that n is n times p times 1 minus p, greater than or equal to 10. And the answer is yes. If you take 40% of this, would be 20 some, and then times 6, about 60. 1 minus p would be about 60%. So it'd be about 18. So yeah, the answer is yes. All right. So you do have to check this condition, and it's real quick. All right. So you pull a sample of size 52, and then you look at the p hats. You look at the sample proportions. Right? Now, by the central limit theorem, since this condition is met, right, this n times p times 1 minus p is greater than or equal to 10. By the central limit theorem, the distribution of the p hats, right, if you were to look at all possible samples of size 52 and look at their p hats, the sample proportions, all those sample proportions would have an approximately normal distribution with a mean of mu sub p hat and a standard deviation of sigma sub p hat, where again mu p hat, the average, the mean of all those sample proportions would just be the population proportion, and the standard deviation of all those sample proportions, for samples of size 52, would be the square root of the population proportion times 1 minus the population proportion divided by the size of the samples. Right? Okay, so this one we already know is about 0.404984, and I will enter this into my calculator. All right, now I just did 260 divided by 642. So this ln value here on the calculator is already p. So I'm going to go square root of the previous answer is p times, and then in parentheses 1 minus the previous answer, and then divided by the sample sizes here are 52. And again, make sure all of that is under the square root. So we're getting approximately 0.068074. Okay. So with a standard deviation of about 0.06, 0.068. All right, and then I'll draw a picture for this, right? P hat here has a norm. All these p hats, all these sample proportions have a normal distribution. So I'll draw a picture of one, right? A normal curve. So I got a number line here with possible values of p hat, and above it some symmetrical bell-shaped curve, normal distribution, where underneath the peak is a value on this number line of of p. Let's say 0.04 or 0.405. If I go to the 3 decimal places there, 0.4049, 0.405. And the standard deviation is about 0.07 or 0.068. So under these inflection points, remember the inflection points, the one where it changes the way it curves, those points should be above values that are 1 standard deviation away from the middle. So that's about 0.07. All right, so this is about 0.475, and this is about 0.335 over here. All right, different values of p hats. And remember, approximately 68% of the area under the curve is within one standard deviation. Okay, but that's beside the point. All right, what we're asked to figure out, right, going back to the problem, is if he pulls 52 store items, what's the probability that 24 or fewer of them are kitchen tools? So what's 24 out of 52? Right, so I'm gonna pull the calculator up. What would be the p hat when 24 are successes? So 24 out of 52 is 0.4615. 0.4615. So what we're trying to figure out, going back to my picture, is we're trying to find this probability. We're trying to find the probability that my sample proportion is 24 or fewer, so less than or equal to 24 out of 52. Or in other words, the probability that p hat is less than or equal to, now 24 out of 52 we just saw is approximately 0.4615. So on my picture here, that would be this area. Now 0.4615 be around here somewhere, right, on the p hat number line, 0.4615, 24 out of 52. And we want the area to the left, right? We want to find the probability that p hat is less than or equal to that. So we're talking all this area here. Okay. Now, I can do this in two different ways. One is using this standard normal table they gave us. Now remember, the standard, that means I need to convert everything to a z-score. Now remember, z-score is just how many standard deviations above or below the mean a value is. So I need to standardize. All right, so back on the back on my page here, I'll call this method 1, using the standard normal tables that they gave us. So I need to take this and do what's called standardizing it. Remember, standardize is just finding z-scores. So I changed this to the z distribution, right? The standard normal, which has a mean of 0 and a standard deviation of 1. And if I do that, right, you got z-scores down here now instead of p hats. And again, a bell-shaped, symmetrical bell-shaped curve where underneath the peak now is the number 0, right? Because the z-score of this is 0. And then what I want is the z-score for this 24 50-seconds, this 0.4615. I want to find the z-score for that. So I'll do that off to the side here. The z-score for that would be 24 out of 52 minus, and then the mean here was 0.405, which was the 260 out of 642. I'm going to leave things as accurate as possible. 260 out of 642, right? This was the population proportion. And this gets divided by the standard deviation, right, which was this value here, the 0.068. Right? So this is that, square root of 260 out of 642 times 1 minus that, and then divided by the sample sizes were 52, right? So I'm going to enter all this. It's going to look crazy, but I'll get a z-score. All right, and then we're going to round this to 2 decimal places. So, calculator here. So, all right, so I already have 24 out of 52. All right, so I'm going to subtract from this the mean of the population proportion, 260 out of the 642. All right, so this is the numerator here. That's 0.056 something. And then divided by, the square root of the 260 out of 642 times, and then parentheses, 1 minus that, 1 minus 260 out of 642, close parentheses, divided by the sample size is 52, and make sure that's all under the square root. So we're getting a z-score of 0.83 if I round that to 2 decimal places. So this value here, this one I have up here for the p hat, this has a z-score of about 0.83. Right. And then we're finding the area to the left of that. Right. So this area I can find, remember on the standard normal table, all those numbers that are given are areas to the left. So I go to z-score of 0.83. So that's this number here, z-score 0.083. So we're looking at an area of 0.797. So the probability that this guy, this manager, he pulls a sample of 52 items, the probability that 24, a few of them are, kitchen tools, is almost 80%, 0.797, and enter all this stuff down here. Okay. So we had P was, now they're asking us to round everything to 3 decimal places. So 0.405, right? That was the 260 out of 642. 0.405. P hat, right? That's the sample proportion. That's 24 out of 52, which we said was 0.4615. Right, so 0.462. The standard deviation of the p hats was that square root of p times 1 minus p, over n, which I found was 0.068, right, 0.068. The z-score, all right, you know what? Let me see if I get the same value here using these numbers. All right, so the z-score would be, you take your p hat there, take the proportion 0.462, subtract the mean, which would be that p, 0.405, and then take this number and divide it by the standard deviation, which, using the number I have there, 0.068. Ooh, okay. So you see this would round to 0.84. Right, this would round to 0.84 for the z-score. And if I look back here, a z-score of 0.84 has 80% to the left of it, 0.880. So I'll use these numbers here. All right, let's see, 0.84 instead for the z-score. Oh no, it said round to 3 decimal places. Round your answers to 3 decimal places. But the z-score should be to 2. Oh, this is annoying. All right, I'm going to see what happens when I leave this as 0.84. And then the area to the left of that would be 0.800, right? 0.800. See what happens. All right, let's see if I use the numbers correctly. Great. All right, so use these numbers when rounded. That is kind of annoying that they did ask to round answers to 3 decimal places, but if you're using the table, you should round z-scores to 2 decimal places because you're only given 2 decimal places in the table. So I guess round all the answers except for the z-score to 3 decimal places. That's a bit annoying. They should probably reword that. I'll send some feedback. You can, at the end of problems, you can always send feedback if something's unclear or something's worded wrong. I'll be sending feedback about a problem like this this kind of problem later. Okay, now that was method 1. All right, that was method 1. Now you can also use a calculator. Right, use a calculator. So if I go up here, and use my calculator, remember method 2 here, I'll say, using a calculator. Now if you want to find an area under normal curves, so method 2, use calculator. All right, remember that's the norm. If I want to find area under a curve, that's normal CDF. And then you put your lower value in the region, the upper value in the region, the mean, and the standard deviation. Now this would be the mean of the p-hats and the standard deviation of the p-hats, because we're looking at this distribution of p-hats. So on the calculator again, I go second, distributions, go to that normal CDF. Now this is a left tail thing. There is no lowest value in this region. So I'll put a big negative number like -99999, right? Something that's clearly way far away from the middle. Then the upper value in this region was my p, that particular p-hat, that 24 out of 52, 0.4615 or 0.4. I'll just do the 3 decimal places like they had, 0.462. The mean was the p, right? That was 260 out of 642.405, right? If I'm going to the 3 decimal places like they had. The standard deviation was that square root of p times 1 minus p over n, the 0.068. And then I calculate, right? And then look at this area coming up here. See 0.7990. See, if you used this, it would have said you were wrong, because it was 0.800 on the table, right? They rounded up to 0.84 for the z-score. So, so back here, if it's not the calculator version, if they're giving you a table, use the table. Round your z-scores to 2 decimal places and use the table, right? Because again, if I used the calculator here, I would have entered 0.799 and not 0.800, and it would have marked me wrong. And then if you do use the calculator and it marks you wrong, it's probably only off by by very, very little. Like I would have been off by 1/1000th here. All right. So if you're given a table, convert to z-scores, use the table. Again, you can use a calculator, but just be aware that you might get marked wrong. Now, if you do get marked wrong a lot, if you're using the calculator and you're coming up and you're very close a lot, 5, 6 problems in a row or something like that, or maybe even 3, send me a message, and I can go in and mark the assignment done for you if I feel like, hey, you've marked off numbers close enough to the right answer enough times. Okay. Yeah, so you can use either one, table or calculator. Okay, so this one's similar. So again, oh no, this one's a different objective. My apologies. This is the other way around. So this is if I'm given a probability, find a p-hat, find a proportion. So this is that inverse norm, right? You're given an area under the curve. You want to find values on the number line. All right, so I'll draw another picture for this. All right, so here a sandwich shop finds that 112 customers they serve during the day, of the 112 customers they serve during the day, 64 purchase a coffee with their sandwich. So I'm going to guess here that purchasing a coffee with a sandwich is a success. The shop owner is trying to decide how many baristas to hire per shift. So in the sampling distribution of sample proportions of size 36, above what proportion will 58% of all sample proportions be? All right, so we are trying to find this. All right, so on a piece of paper here. So this time, p hat. Right, this time p hat represents the proportion of a sample of 36, a sample of size 36, they get coffee with a sandwich. Right. And by that central limit theorem, because sample size is reasonably large, right? Usually it's 30 or more, but by the central limit theorem, these proportions, the p hats, should be approximately normal with a mean of p, which we'll find, and a standard deviation of the square root of p times 1 minus p divided by n. Again, we'll find these things. All right, so the mean of the p hats, again, is p. Now, what was the population proportion? All right, so they said of all 112 customers, that's the population they served during the day, 64 purchased coffee with a sandwich. So 64 out of 112 is the population proportion. 64 out of 112. All right, and we'll round this. Now, it doesn't say anything about rounding. It just, so I'll leave it as 64 out of 112 until the very end, and then our choices are rounded to 2 decimal places, it looks like, but it doesn't say anything about rounding. Now, 64 out of 112. 64 divided by 112 is 0.57, right? So approximately 0.5714. So the population proportion, which is also going to be the mean of the sample proportions, is a little over 57%. All right, and the standard deviation of these p hats, the standard error, is the square root of this times 1 minus it, and then divided by, in this case is 36. All right. So let me enter this. All right, so on the calculator here, again, I'll just do the square root of the previous answer, right? The previous answer was the population proportion times, and then in parentheses, 1 minus that previous answer divided by 36, right? All of that underneath the square root. So we're getting a standard deviation of approximately 0.0825. If I go to 4. Right. Now if I'm going to be using this again, all right, I am going to be using this value again when I do z-scores. So what I can do if I want to use it again is I'll store it as another variable. If I store it as x, say if I hit the stow button and hit the x variable button, now every time I hit the letter x, it'll be that number. So I don't have to keep retyping it. All right, so x represents the standard deviation of the p hats now. And I'll make a picture. Here are all possible values of these sample proportions, for samples of size 36, normally distributed, right? So I got this symmetrical bell shape here. The mean is over, 0.5714, the population proportion. And then these inflection points, right? These are about 0.08, let's say about 0.08 above. So this is approximately 0.65-ish, and this is approximately 0.49-ish, right? And about 68% between these two, right? These are 1 standard deviation above, 1 standard deviation below. But now, what we're given, though, right, what we're told, well, what we're asked about is, above what proportion will 58% of all sample proportions be? So we're looking for one specific value on the number line that has 58% above it. So say about in here, what is this? P hat equals question mark. What is this value such that there are 58% above? Right, so this area is 58%. That means that the area to the left, that means that this area here, sorry, it's getting kind of faint. That means that this area here, if there's 58% above this value, there's a 42% below it. Okay. All right. Now again, there are a couple ways to find this value. Method 1 would be to use a table. Method 1 to finding this value is using a table. Now the tables give us z-scores. So again, method 1, table. So let's find the z-score for this. What's the z-score? So I'm going to look for the z-score that has 42% below it, right? Now that's because remember, on a table, all the numbers given are areas to the left, areas below. So I'm going to look at these areas and look for the one that has, the closest to 42% below it without going over. So you see this. So see how negative 0.10 has 46% below it. That's too much. So look here. Negative 0.20 has 42.1% below it. But that's too much area as well. So the closest to without going over is a z-score of negative 0.21, which has 41.7% below it. So back on the paper, this value I'm looking for has a z-score of approximately negative 0.21 according to that table. And then I just need to find p hat. Find p hat. Now remember the formula for z-scores, right? The z-score for any particular value was that value, so that p hat minus the mean value of the p hats divided by the standard deviation of the p hats, right? And we know these. And then I'm solving for p hat. I'm solving for this. So the p hat would be the z-score times the standard deviation. I would multiply by the standard deviation and then add the mean. All right, so let's do this. So I'll pull up the calculator, which I already have. So I take the z-score, which I'm saying is about negative 0.21, multiplied by the standard deviation of the p hats. Well, I already had that here. I'll just put in the previous answer. That's already there, and then plus the mean. Now the mean value, that population proportion was 64 out of 112. That 0.5714. All right, we're getting about 0.554. So this is 0.554, right? So the sample proportion of 0.554 has about 42% below and 58% above. All right, and look at this here. So you see about 0.554 right there. That's the p hat. The z-score is negative 0.21-ish, right? So this here and this here. Those are the values I used and found. Now, that was one way to do it, right? Using the tables. The other way would be using a calculator. Now, if you recall, when you're given an area under a normal curve and you want a particular value on the number line, that was using that inverse norm. Right, so method 2, remember the inverse norm on your calculator, where you enter the area to the left first, and then the mean of the p hats, then the standard deviation of the distribution, the standard deviation of the p hats. All right, so for this particular picture, I'm on the calculator. We go second, distributions, and then down to number 3 there, right? That inverse norm. Remember, this area is area to the left. Now the value we're concerned with has an area to the left of 42%. So I put 0.42. The mean was this 0.5714, or that 64 out of 112, right? That was that population proportion. And then the standard deviation, and here's why I stored this. X. Remember, X was this value, this 0.0825. Now I could put 0.0825, if you want. But remember, I stored that as the letter X, right? X up here on my calculator was 0.0824, blah, 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 right? Enter. And you see it's 0.5, look at this, 0.554. It's the same value to 3 decimal places. So 0.55, this particular p hat would have to be 0.554, 0.555 to have 42% below it and 58% above it. So that was that, again, that inverse norm, when you know an area under the curve and you want values on the number line. Okay, great. Right, so again, now hopefully, now you had to find the z-score here, so you did kind of have to go and find the z-score, like I did. Okay. Again, they show you the whole procedure again, right? Finding the z-score on the table, using it to determine, to determine the particular value that has that 42% to the left and 58% above. Okay. All right. This is again using the central limit theorem for proportion defined probabilities. I have done a problem like this already. All right. Let's go back to that problem where I had this objective. I've done this one already, something like this already. So I'm just going to cheat on it. Now you have to figure out certain values. What's the population proportion? What's the sample proportion? What would be the standard deviation for the sample proportions, right? That was that square root of p times 1 minus p over n. The z-score would be p hat minus p divided by the standard deviation, right? The value minus the mean of the p hats divided by the standard deviation of the p hats, and remember, the z-score should only be to 2 decimal places. I know it says, see, round the z-score to 2 and all other answers to 3. See, they should have had this on the other one. So z-score to 2, all the other answers to 3, and then what's the probability of being, less than that z-score? So find that on the table. I've already done something like this. So I'm just going to have this be cheating yeah. Oh, you don't have to enter the plus or minus 0.001. Yeah, it looks like they're going to allow you to be off by, so maybe you could use a calculator here. Maybe you could use the calculator, and it looks like they're allowing you to be off by so much, by 1,000th on either direction. Yeah, you don't have to worry about entering the plus or minus 0.001, okay? Yeah. And this is another one where you're given an area under the curve, find a proportion, finding a z-score, and finding a particular value that has a certain area to the left or a certain area to the right. So again, I've done something like this already. Go back and look at that problem. It'll be done in exactly the same way, either using the table or that inverse norm on your calculator. Okay. And again, this is no different. This is finding area under the curve. All right, so this is finding areas under the curve, either again using a table, use a calculator with the normal CDF. And again, don't worry about writing the plus or minus 0.01. If you just put 0.8, that would have been fine. And this one is, again, you're going to use normal CD. Oh, this one's an actual graph, right? So let me do this one, because you have to move some stuff around here. So here, according to a study, 40% of people have more than $10,000 in credit card debt. So this 40% is like the P. the population proportion. What proportion of people have more than $10,000 in credit card debt? Here, having more than $10,000 in credit card debt is a, success. So P is 0.4. Suppose that in a particular bank, there are currently 60 customers waiting in line. So there's your sample, the 60 customers in this bank. So N is 60. So use the graph below to calculate the probability that of those customers, of those 60 customers, between 21 and 23 of them have more than $10,000 in credit card debt. Alright, so first we drag and move the blue dot to select. Now this is a between thing, between 21 and 23, so this will be one of those interval probabilities, not a left tail or a right tail, but we're between two values. And so that'll be that last graph down here, right, like that. Okay, and then use the central limit theorem to find p hat and then the standard deviation of p hat. Now p hat, I think they meant the mean of p hat. Yeah. Well, the standard deviation, I'll pull a calculator up. The standard deviation of p hats for samples of size 60, right, samples of size 60 would be the square root of p. I'll pull square root of p, which is 40%, 0.4. They told us that, right? Times 1 minus p would just be 0.6, divided by the size of the sample, which is 60 customers here. All right, so the standard deviation of the p hats distribution is 0.0632. Again, I'm going to store this as x, right? So now every time every time I use the letter x now in my calculation screen, it's going to be that 0.06 above that. All right. Okay, so I'll enter that, and we got the standard deviation of the p hats to how many decimal places do they want? 2. All right, round your answers to 2 decimal places. So 0.06. 0.06 for this standard deviation. And then the probability that we're getting that the number of customers between 21 and 23 of these 60 customers have $10,000 in credit card debt or more. Well, you see on the graph here, we have to move the z-scores. So what's the z-score for 21 out of 60? And what's the z-score for 23 out of 60, rounded to 2 decimal places? All right, so z-score for 21 out of 60. So I take 21 out of 60, right? That's the p hat. And I subtract the mean. I subtract 0.4, right, the p. And then divide this by that standard deviation, which I called x, right, the 0.06. So the z-score for 21 out of the 60 customers having $10,000 or more dollars in debt is negative 0.79. So I'm going to move this left dot to negative 0.79. All right, and then the right dot will be at 23 out of 60. So what's the z-score for 23 out of 60? So I take 23 out of 60, and then subtract from that the mean, 0.4, the value of p, and then divide this by x, right, 0.06, the standard deviation. So we're getting negative 0.26, right, negative 0.26 for the z-score of this right value, the 23 people out of 60. So negative 0.26. 4, 5, 6. Oh, come on. There you go. And the area between them is going to be our probability. The probability that between 21 and 23 people out of 60 have a debt $10,000 or more, about 0.1826, which rounds to 0.18. Right, just says round all your answers to 2 decimal places. Right. So approximately 0.18, about 18%. Calculator, submit. Wonderful. Right. So hopefully you understand what happened here. Right. First, you got to say, well, what kind of area am I going to have? A left tail, a right tail, outside two values or between two values. And then you move the dots on the black dots here to what are the z-scores for those values. And then it gives you the area, and you round the area to whatever number of decimal places they ask you to round to. Again, you do not need to write the plus or minus 0.01. That's just kind of their tolerance. So if I put in 0.17, it would have been fine as well. 0.16 would have been fine because it's 0.17, give or take 100th. So that's why 0.18 counted here. So yeah, some answers have tolerances and other answers don't for some reason, but it worked out this way here. All right. So this one, another one where you're, find a proportion given a probability. So this is another one of those where you're given an area under the curve, areas under the curve, and you're finding certain values on the axis. So you can use the table there, or like I did in an earlier problem, or that inverse norm. That might help as well. All right, so I'm going to cheat on this. You've seen me do a problem like this already. And then here's another one where proportion given a probability, so that inverse norm, or using a table. Again, you've seen me do a problem like this already, so I'm just going to have this be cheating here and moving on. All right, now the last two objectives are just doing the same thing, finding an area under the curve or finding a value on the number line when you know an area using your calculator, and I've already shown you how to do that. All right, I've already shown you how to do that using normal CDF or inverse norm. Okay, so I am going to skip these again. All right, and I'll show you in the answers. Just again, pay attention to how many decimal places they want things rounded to, that's all. So you see how they're using normal CDF here, and I've already shown you that. This is the same thing, same kind of problem. And you got to find the standard deviation for the p-hats and then the area between two values. Oh, this one's the same problem as earlier, only now they're not having you move stuff on a graph. So this should be like 0.1816 or 0.181 or 162 or whatever I had earlier. All right. All right. And then again, see how they're using normal CDF here. Normal CDF. And again, notice there's no plus or minus on this. So it's weird that some problems have tolerance and some problems don't. So again, if you're getting really close, if your answers are very, very close to answers they're given, just send me a message and I'll look at them. And if I've seen you done enough where you're close enough, I'll probably just mark that assignment done for you. And this is the objective where it's the other way around. You know a probability, you want a proportion. You know an area under the curve, and you want to find a proportion. This is going to involve that inverse norm. All right, so you see, find the proportion above which, with 65% above or 35% below. I did this earlier again. All right, only this time you don't have to use a table. You can just use that inverse norm. So again, I'm just going to cheat. I've already shown you a problem like this. And again, you're seeing the inverse norm down here. Yeah, so the rest of the problems should be similar in one direction or the other, using normal CDF or inverse norm, depending on what you're being asked for. Just kind of scanning through here just to make sure there's no other different kinds of problems. So far there aren't. You've seen me do a problem like all these before, and again, these are just now with the calculator only, and the tables aren't given. So yeah, this one will involve another normal CDF. Right, area under a curve, fill in the blanks here, round to 3 decimal places, all that good stuff. And use the answers rounded to 3 decimal places in your calculations with the calculator. Right? That'll probably get you the answers they want. And it looks like I got a couple more here where you're given an area, finding a value. This is that using that inverse norm, and again, round your, pay attention to how many decimal places. Get this up. And if at any time, you can pause the video and read through what they have here, and figure out how to do these things if you didn't see me doing it earlier, or pay attention earlier, or you didn't understand earlier. Maybe you can read through what they have here, how to use the inverse norm on your calculator to find certain values. And again, use the values rounded to the decimal places that they have, and should end up with the answer they want. All right, so a lot of stuff there. I know there's 5 objectives. It's one of the longer assignments, but you notice that the 2 objectives where you're finding area under a curve or finding a value on a number line, those are just repeated again with the calculator. So you're doing the same thing a lot, same thing over and over again. All right, so again, if you're having any issues, if you're really close on certain problems, you're doing it right, but you're getting it off on the last decimal place and it doesn't have any tolerance, let me know if that's happening a lot to you, and again, I can go in and check it out and take a look at your problems, and if I feel like it's happening very often, you're still incredibly close, I'll mark the assignment as done for you. But try your best to get them right, nail them the way that they want them first time around. All right, and of course, if you have any questions on how to do any of this stuff, let me know. And thank you very much for watching. Hopefully this is a good guide for you when you work on this assignment on your own. Thanks.